Okay, I'm going to go through our Camp Sunshine analogies, which is going to be based off of our next topic in our unit to this point. In Camp Sunshine, we are responsible for putting campers into correct bunks. And in order to do that, we have a couple of ground rules. And our ground rules are as follows. Campers are picky. They want to be closest to the mess hall first. Campers want their own cabin when possible, only doubled up as needed. And the first campers in a cabin prefer the top bunk. And the second campers will take the bottom bunk. And so let's say that we have a bus carbon coming in. And bus carbon is going to bring with it a certain number of campers that we have to account for. And so we can look and use our table here, periodic table, as our guide, and we see that carbon, which is atomic number 6, is going to bring with it 6 campers. And so we say, okay, let's account for them, and let's abide by the ground rules of the camp. Mess hall is closest to us, and then we see that the first cabin is the 1S cabin. We're going to place a camper up on the top bunk. We see that we have to double up before we can move on to the next bunk, and therefore there are 2 campers there. Then we do the same thing with the 2S cabin, and then we get to the 2Ps. We have 4 campers already accounted for. And remember, they want the top bunk when they're the first, but they also don't want to be doubled up if they don't have to, and the 2P cabins come in 3s, and so we can put our 6th camper there. So what would the camper's full address be? Well, if they want to send mail or they want to receive mail, we have to make sure that people know where they are on our campground. And so when we go through, we just place our initial cabin that we first occupied, and we add the campers that are in there. All right, there are 2 total campers. Then we keep going and we branch out as we get further from the mess hall. And so the next cabin we filled was the 2S cabin. And then we got to the 2P cabins, and there are 2 campers occupying those. And so sometimes we want to abbreviate this, and we can abbreviate by basing it off of the most recently filled up dirt road. And you can see these dirt roads are numbered, and that's going to be based off of the row that we look at on the periodic table, or what we call a period. And so what we can do is we can say, well, which item on the periodic table allows us to see the first 2 campers and to account for them. And so based off of the atomic number and how we identified how many campers were coming to begin with, we're able to identify, well, which element is number 2. That's going to take care of the first 2 campers, and we see that that is helium. And so what we can do is we can go back, and then we can identify that the first 2 campers here, the 1S2 cabin, are actually going to be replaced by just writing in that helium symbol there in brackets. And then we add on the campers that are left over. And so that's how we can shorten it. Now, it doesn't make sense to shorten such a small amount of campers right now, but as we get more buses that come in with many more campers, it'll be a lot easier then to see why we do that. And then the campers that live on the furthest road, again, the road is based off of the number here, and so what we're going to do is we're going to look at the second road, which is the farthest road that we have campers occupied, and there happens to be 4 there. Next up, we're going to go look at magnesium. Magnesium is going to bring over with it 12 campers, and we know that because magnesium is atomic number 12, and so we're going to account for those 12. And so 12, abiding by our rules, our diagram starts to look like this. Now remember, they want to occupy by themselves first, and we do have to end up doubling all of them up, and then we move on to the next dirt road, and we end up needing to fill that 3S cabin as well. And now I have all my campers accounted for, all 12. So what's the full address? Well, we do it exactly how we did for carbon. The only difference is we have more campers to account for, and we filled up more cabins. And we do, again, in order in which we have filled them up. Now for the abbreviated, we do the same thing, and we see that the most recently filled in dirt road was the second dirt road, right? And so we look over on our periodic table to identify, well, what marks the second dirt road filling up? Well, the second dirt road represents the second period on the periodic table, right? Here are our 1s1, 1s2, and then here was our 1p1, 1p2, 3, 4, 5, and 6. And so what we see is that the 2p cabin ends where neon ends. And so that is going to be our abbreviator, so to speak, for this one. So we're going to go back. We have 1s2, oh, almost erased everything. 1s2, 2s2, 2p6, that is 2, 4, and 6 is 10. That means that the first 10 campers can just be replaced by writing NE for neon in brackets. And the campers that are left over go on the outside. How many are on the furthest road? The furthest road is the third in this case. There are only 2. And we do the same thing for potassium. We go back, we identify how many campers there are going to be. We identify potassium as atomic number 19, which means there are 19 campers. And so we account for those 19 campers by placing them in the order in which we did before. The only difference is we are going to occupy a further bunk. And we keep going, and notice anytime there's multiple cabins in an area, I have to single each camper before I double them up. And then we end at the 4S and with only 1 there. So we say, okay, well, the address is 1S2, 2S2, whoa, 2P6, 3S2, 3P6, 4S1. Now you're seeing how we end up with more dirt roads filled, and the more dirt roads filled, the longer our address is. And so the most recent dirt road that we filled was the third road. And so we go and see, well, how many campers do we have all the way up until the third road ends? And we see 2, 4, 10, 12, and 18. So we're looking for the element that has the atomic number 18, which ends up being argon. And so argon is going to account for the first 18 of those campers in our bunks. And so we say, okay, all of that is argon. And if you wanted to color code it or highlight it, if that helps you, you can. I know I didn't do it on this one. I probably should. Right? And I think it's just nice to be able to kind of have that visual as well. And so I'll do that for that one too. So you can see how argon accounts for all those, and now all we have to do is write the campers that it doesn't account for, which is the 4S1. And now the furthest road we see is 4. And so because of that, we see that there's only 1 camper in there. Right? So what does this all mean? Well, in terms of the bus, you've probably guessed that it represents the element in which we're working with. The campers, initially, you want to say are the protons, because we're using the atomic number, and atomic number equals protons. But remember that atoms are neutral, which means that the number of protons is equal to the number of electrons. Now we're talking about placing these campers further and further away in these cabins. Well, if I'm talking about an atom, then the things that get placed further and further away from the center are the electrons. And so the campers are actually the electrons in this case, because we're assuming all of these are neutral atoms. The farthest campers are, of course, our valence electrons, right? The ones that occupy that furthest shell. The mess hall is then the nucleus. The nucleus is where the protons and the neutrons are, and that doesn't change, right? What changes for our orbitals is how many electrons are occupying, because those are what are on the outside. The cabins are what we call orbitals. The dirt roads are what we call energy levels. And so certain energy levels are going to have certain numbers of cabins and certain amounts in each. And so we're able to kind of identify that through those dirt road analogies. The camp cabin diagram is the orbital diagram. It's kind of just like a schematic of where those campers are. We also have a Bohr model that helps us do that. The full address is what we call the electron configuration. And the electron configuration is just our best kind of idea of where these electrons are residing in an atom, because we truly don't know. But with these models, we're able to at least predict that this is where they should be, and these are the orbitals that they should be occupying, orbitals and subshells. And then we have the abbreviated address. And what you'll notice is all of our abbreviated addresses began with a noble gas, because our noble gases are what mark the ends of our periods. And so what we do is we say that the abbreviated address is called the noble gas configuration. And this is a little bit of information just to kind of visualize the periodic table, and note that this section is actually the section that we see at the bottom of our periodic tables. And so if I'm looking, it's this section right here. And there are different blocks. There are different subshells based on where these orbitals exist and what energy levels they are occupying. And so what we can do is we can actually identify them by looking at the periodic table in blocked sections. And so we really won't talk about that F subshell down there. But what we will do is talk about that top part. And why you see it the way that it is on the worksheet is because that's actually what the periodic table looks like if you stretch it out. But of course, that would be just too long and obnoxious to have on you like at all times for chemistry. And so what they did was they condensed it. And because these all have relatively similar properties, they just put them kind of underneath as like a way to save space. And so we look over here, and you'll notice that here there are stars that correspond with these, and then you notice it goes from 56 to 71 up here. That can't make sense. Oh, 56 and then 57 is down here. And so these are actually kind of supposed to be integrated into the periodic table itself. We just treat it as something separate because we're able to kind of do that. And so we're going to be focusing on the S, P, and D blocks ourselves. And then we notice that with our noble gases and these outer campers, so to speak, that those are representing our valence electrons. And so what we can do is we can say when we have a noble gas configuration, whatever campers aren't accounted for are going to, more often than not, represent the valence electrons. Now, in order to do that, because we're going to get into instances where we actually have some core or inner campers kind of there as well, not accounted for by the noble gas, we have to look at the number. And the number is going to tell us the higher the number, the further away they are. So let's take a look at an example here. I'm going to leave a couple examples for you to do on your own to practice, but I'm going to do tin just because it's a little bit bigger of an atom, and it's going to bring a lot of electrons with it. And so when we look and we find tin, and I'm going to use this periodic table actually, we see that tin is number 50. And so we have all of these different subshells that we see. We have the S's, we have the P's, we have the D, and we have the F. Now we read the periodic table pretty much like a book. And so that 1s1 cabin that we always start with, that's hydrogen right there. And so we're basically just counting until we get to the element that we're looking at. And so 1s1, you'll see that helium is actually a part of the S block. Now, of course, it's over here, right? But I just wanted to make sure that you know that helium is a part of this S block over here. So that's why I'm kind of showing you that. But that is our 1s2, and once we fill that up, we move on to the next one. So it's very similar to how we did our Bohr models. So then when I go through, I'm labeling 1s1, 1s2. This is 2s1, 2s2, so on and so forth. Then I enter this block over here, this blue block. These are my P's. And notice I can fit up to 1, 2, 3, 4, 5, 6 electrons in the P subshell. And so what I can do is I can say, oh, okay, well, I'm just going to write everything in order in which I pass it, right? So I had 1s1, 1s2, And then I have 2s1, 2s2, 2p1, 2p2, 2p3. And these don't change, right? Because the periodic table doesn't change. 2p4, 2p5, 2p6, and so on. Now, of course, we don't write all of these in that order. We just write the very ends of those, right? We only write 1s2. And once we filled it up, that's what we put in our configuration, and then we move on. And so as we keep going, you'll see we get to, and I'll try to do this with a highlighter here just so you see. So we have 1s2, 2s2, 2p6, then we move on to 3s2, 3p6. I'm still not at 10 yet. I move on to 4s2, and then we stop. We get to these, what we call transition metals, and this D subshell, this block that's green, is actually delayed. So all of the electrons that are right here or right here, those are actually a part of the previous energy level, right? These over here on the side, these period numbers are our energy levels. And so these D's are delayed. They actually go backwards into the previous energy level. And so that's why you see I have 3D right there. And so what's going to happen is after 4s2, we end up at 3d1. And then we keep going. You see, we can fit more than we could even in the P's, right? We have 3D1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. Once we fill up that D subshell, the third energy level is now finally full. And we then enter sorry about that, the 4P. And so it goes back to kind of like your regularly scheduled program. And then we have 4P1, 4P2, 4P3, 4P4, 4P5, 4P6, and then I'm still not at 10, right? And so I keep that going, and it's the same pattern over and over and over again. And so if we know what the blocks are, then it's going to help us out a lot. But what also will help us out is our cabin diagram or our orbital diagram. And so I basically want to use that at first to help me out. So total electrons is 50. Here's my cabin. You can see that the 3D is in between the 4S and 4P, just like we had mentioned. The same goes for 4D, right? D's are delayed. That's why this D, even though it's between two 5s and the 5th road, so to speak, it's actually a part of the 4th level. And this is what can kind of get a little confusing because you're like, well, why doesn't it go in order? And that's because even though 4 is a greater energy level, these electrons in this D subshell actually do have a little bit more energy than the S subshell. And because of that, we're able to kind of put them back into the third energy level because the third energy level is effectively big enough to hold them. All right, so then we have to make sure that we put them back in. And so what we do is we can fill out our cabin diagram until we hit 50. And I'm going to do that. 1, there's 2, here's going to be, that's 10. Here's 12, 14, 16, 18, right? This would be argon. All right, that would be calcium. All right, 20, 21, 3, 4, 5, 7, 8, 9, 10. There we go. Here, we have to keep going because we are going to hit the 5S. We have so far 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, 32, 34, 36, 38. And we keep going. This is going to be 48. This is going to be 49, and this is going to be 50. And that would be ending at 5P2. So I'm going to write all of this in the full configuration, as now you see that noble gas is going to come in handy. So we have 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, because the D's are delayed, so they're a part of the third level. And then I'm just going to keep going on the bottom underneath it. 3d10, then we get to 4p6, and then we get to 5s2, and we have to go backwards again, 4d10, because the D's are delayed, and then we get to 5p2. The cool part about this is that if you look at our periodic table, right, here's tin. It is the second element in the 5p. So this would be 5p1, and here's 5p2, which is exactly where we ended. That's awesome, right? And so, I'm effectively reading this periodic table like a book. And as I go through from top left, row by row, I'm able to actually get to where I need to go in terms of what element I am at, and then what subshell or what block it is in. All right, and so kind of going back here, we want to know the noble gas configuration. And so if tin is here, then I want to make sure that I identify, well, what noble gas came from the row or the period before it. And what we see is that the noble gas that has come before it is krypton. And so krypton, being number 36, is going to account for the first 36 electrons. And so you can think of it that way, or you can think about krypton being 4p6. And so it's going to take up everything until 4p6. Whoops. Well, I don't want to paste that, but now I don't know how to get rid of it. So now we go over here and we say, okay, this is 4p6. So I'm going to highlight up until 4p6. And all of those are going to be taken care of by just writing in krypton, which is fantastic, because now the only thing that we have to leave or put in next is whatever is not a part of that, which is 5s2, 4d10, and 5p2. And now before, we would say, okay, how many valence electrons? Well, it's basically whatever's left over. But remember, we have to identify the furthest energy level. And now, although the D subshells do get filled in before the P subshells, they are still not part of the furthest energy shell or ring. So we have to base it off of that number, right? What is the highest number here? We see the highest number is 5. That's the furthest shell, so I only include those electrons, which ends up being a total of 4. Right? And so that's how we can identify valence electrons when you have these weird D subshells kind of mixed in there. All right, so you can try out those other two yourself as well. And I want to do one more example with you. In terms of connecting these, I said that, we have these diagrams here that help see where these electrons are. But we can also use our Bohr models that we were familiar with to also represent. And it kind of helps with the electron configuration, seeing what we would need to put back in to that like third or fourth or whatever energy level when we get to that D subshell. And so here we're looking at vanadium. Now, if I look at the periodic table, I identify where vanadium is. Vanadium is atomic number 23, so it's going to have 23 protons, which means it's going to have 23 electrons. And so I look and I say, okay, 23 electrons. I know that I start with 1s2, I go with 2s2, and you can also write 23 electrons here if you want. And maybe you're like, oh, wait, I forgot where those electrons are, or what's next. You can always either use the periodic table to help you, or you can draw your own diagram like we did before, right? You can do that even if it's not there, just to help you. So I'm going to go look and I'm going to say, oh, I got stuck. I have to look and see, okay, I have my 1s2 here. I have my 2s2 here. Oh, yeah, I go to the 2p's. So that's 2p6 at neon. And then it's 3s2. Then it's 3p6. And then it's 4s2, and then I get into the D's, which are 3D. So really, what I'm doing is I'm ending my electron configuration at 3D3, because vanadium's the third in that 3D subshell. And so I go over here, and I say, okay, 1s2, 2p6, 3s2, 3p6, 4s2, 3d3. What's the noble gas configuration? Well, we identify what the noble gas is. We see that vanadium is in period 4, so we're looking at the noble gas in period 3, which is argon, which takes care of the first 18 electrons, or you can think of it as the 3p6, up to 3p6, right? All of our noble gases, well, let me do that a little bit better. Of course, except helium. Helium's weird, right? But all of our noble gases end with P6 as their final configuration. And that shows us that marks the end of a period, right? P6, because I have the 2 from the s orbitals, that's showing me that 2 plus 6 is 8. 8 is the most valence electrons I can have until I have to move on to the next shell. And then I say, okay, well, the first 18, or 3p6, was all of this. And so all of that is going to be taken over by just substituting argon. And we do use brackets, not parentheses. That is just notation. And then we tack on the 4s2 and the 3d3. All right. Now, let's draw this out as a Bohr model. And I tell you it's 51, so we know how many protons and neutrons should go into the nucleus. So this, remember, is the mass number, or the atomic mass. It is not the average, it's just an isotope that we're looking at. And so what I'm going to do is I'm going to draw my nucleus, because every atom starts with a nucleus or a mess hall. And then I'm going to put protons and neutron amount. Now remember, because vanadium is atomic number 23, it has 23 protons, so I know that's 23. And then I say, well, how can I find out how many neutrons? And remember, the neutrons and the protons make the mass. So if I know the mass, I know the protons, I just subtract and I figure out how many neutrons there should be. So in this case, there should be 28 for this isotope of vanadium. Now I have to identify how many energy levels I am going to have electrons occupying. We find the energy levels based on the period in which it resides. And so we say vanadium is in the 4th period. And so we go and we put 4 shells around our nucleus. And I'm doing it with dotted lines just so that you can see the difference between the nucleus circle that you draw and the shells that we draw. And then we start to plug in. In terms of the electrons, remember when we were going through the Bohr models, we were identifying based on each shell and each period, it can only hold a certain amount of electrons. Like the first shell represents the first period. Well, there's only 2, and if I get rid of helium here, just so that it doesn't confuse, right? There's only 2 elements in the first period, which means a maximum of 2 electrons can fit there. So I know that 2 electrons, you could draw dots if you want. I think it's a little easier to draw just the number so that you have it as a placeholder. There are 2 electrons in the first shell. And then I move on to the next one. And what I notice, and I can use the electron configuration here, right? This is telling me, and I think this is really cool, is that if you look over here, the first ring has 2 electrons. Well, the second ring has 2 plus 6, which is 8. And then that gets full. And then the third has 2 plus 6 is 8. And then the fourth I see has 2, right? And so you can use your electron configuration to help you place these electrons where they want to go. The problem is we're missing a couple of electrons because of this D subshell. But remember, the D subshell is actually a part, is part of the 3rd energy level. And because of that, we now have to put 3 more into the 3rd energy level with the 8 that are already there, because a total of 18 can fit in that 3rd level. So when you're looking at something like the electron configuration, that is how you can go about filling the electrons in backwards, right? Remember, these have to be in the 3rd level because of how the D subshell acts. Right? And then, of course, we have our Lewis dot representation, right? Our Lewis dot is quite literally just the element symbol, which in this case is V, and the valence electrons. Well, how many valence electrons do we have? Well, the valence electrons are the furthest away. The furthest shell occupied, the first row, or the furthest road that we have from the mess hall, right, is the 4th. And there are only 2 electrons there. So when I'm talking about valence electrons, I'm talking about the furthest ones that are furthest away. And in that case, it's just 2. So even though there's that 3D3 there, remember, it's based off of the highest energy level, not by the furthest that I draw out. And so to do the dots, I just place 2 dots on opposite sides or different sides. Remember, just like in our cabins, they don't like to be paired up if they don't want to be. So you can do strontium on your own, and then there's a little certification exam, not an actual exam, but just some more practice with all of those topics. So I hope this helps. I know it was a little long, but electron configuration can take time. So do your best. If you have any questions, always let me know. See you later.